So, hello, can you hear me? I would like to welcome you all to this year's Lise-Meitner-Lecture given by Professor Claudia Draxl from the Humboldt-Universität of Berlin. It's a truly great pleasure to have at least a few people here in the lecture hall again. And we're one step further into normal academic life, I would say. Some of them still seem to be a little bit used to streaming, so we hope that much more will be listening online than are actually here in Lecture Hall A today. I don't see how many people are still in the other lecture halls, but anyway, just let me welcome again also the German Physical Society people. The president of the German Physical Society will be listening to the talk online, and I hope a lot of colleagues from Germany as well. And we have the pleasure to have the rector of the University of Innsbruck here, who will say a word or two a little bit later. And we have the president of the Austrian Physical Society here in person. As you have been looking at the screen here, if you have looked at the screen, you see the Lise-Meitner lecture is a joint venture of the German Physical Society and the Austrian Physical Society. We have been doing this lecture series since 2008, and we had really truly outstanding female lecturers who we think serve as excellent role models because they are also cool personalities, not just cool researchers. It started off with Millie Dresselhaus, and then we had people like Cecilia Jarlskop, very famous high-energy physicist. We had Anna Frebel, a young astrophysicist. We had Renate Loll, who does quantum gravity models. We had Dame Belle Burnell, who has made breakthroughs in astrophysics. Felicitas Paus, a person who is from Austria but was a leading researcher at CERN in relation to the discovery of the Higgs particle, for example. We had Cornelia Denz, Petra Schwille, and Nicholas Spalding from ETH Zurich, last year from Australia, Halina Rubinstein-Dunlop, and today Claudia Draxl. So what was the intention of the Lise-Meitner lecture? And my colleague, the president Maurizio Musso, will say a little bit more on this. It was the idea that there are very many very great female physicists who do outstanding work and are really great personalities out there. And we'd like to draw the attention of the public, and especially young people, to this type of personalities. And we hope that in Germany and in Austria we can inspire young people to pursue physics and to see what a nice thing is to be active in this kind of research field and do also things that are important for society. Especially today's topic will be related to this. And with this, I hand over to the rector, who will maybe say just, I don't know, a word or two.
Ja, ich wurde spontan informiert, dass es diese Lecture gibt, und es ist tatsächlich auch für mich jetzt die erste Präsenz-Lehrveranstaltung wieder, an der ich teilnehmen darf. Wunderbar, aber noch wunderbarer ist sozusagen der Inhalt, die Vortragende und der Titel dieser Lehrveranstaltung. Ich selbst stamme ja noch aus einer Generation, die Lise-Meitner sozusagen noch erlebt hat gewissermaßen. Ich habe promoviert in dem Jahr, wie Lise-Meitner verstorben ist. Für mich war Lise-Meitner eine wichtige Bezugsperson insofern, als dass ich ja noch die Folgen und die Konsequenzen der Erklärung ihrer Entdeckung ja noch direkt mitbekommen habe als Kriegskind. Und insofern war also die Kernspaltung und die Radioaktivität für mich auch als junger Student der Physik prägend. Ich habe selber noch im Rahmen meiner Dissertation über Radioaktivität dissertiert. Also für mich war das immer ein wichtiger Bereich und ich habe es eben damals und immer noch jetzt sehr schade gefunden, wie eben das damals gehandhabt wurde mit der Vergabe des Nobelpreises. Und weil ich hier jetzt sehe, jetzt ist es weg, dass der erste Vortrag hier über Carbon-Nano-Dinge war, für mich erinnert das an die Entdeckung des C60, wo ja auch nicht für die Entdeckung, sondern für die Erklärung der Entdeckung, was C60 war, der Nobelpreis vergeben wurde. Und insofern war das natürlich damals eben wahnsinnig nicht in Ordnung, dass also Lise-Meitner eben nicht den Nobelpreis bekommen hat. Aber wie auch immer, wir sind jetzt in einer anderen Zeit und ich freue mich sehr, dass also wir das jetzt nützen können für uns. In Innsbruck ist nach wie vor ganz, ganz wichtig, dass wir mehr Frauen in den MINT-Fächern zum Studium verleiten können, zum erfolgreichen Studium dann führen können und dann auch unter den Kolleginnen begrüßen können. Und insofern wunderbar, dass Sie heute da sind. Alles Gute für den Vortrag.
So, before I introduce the lecturer to you, a few words by our president.
Okay, my name is Maurizio Musso. I'm for this year and next year the president of the Austrian Physical Society, and I enjoyed very much the conference which was held jointly by the Swiss Physical Society and the Austrian Physical Society about 3 weeks ago, exactly in these rooms. Yes, it was a very successful event, and I hope this will continue in this way. And in particular, very important also this Lise-Meitner-Lecture as public lecture in order to attract persons to the field of physics and the concepts of physics, as they were already shortly presented by the picture before by the person who presented this in the last years. About the Lise-Meitner-Lectures. The Lise-Meitner-Lectures are a series of public lectures in honor of Lise Meitner. She was born 1878 in Vienna and died 1968 in Cambridge. And the one important point, she was the first woman at the University of Vienna and the second in the world to earn a doctorate in physics 1905. Yes. And so the lectures are organized jointly by the German Physical Society and the Austrian Physical Society with the intention to showcase outstanding female scientists in physics or in related fields. In order to reflect this, let's say, previous activity which was done by Lise Meitner. And on the occasion, on the 130th birthday of Lise Meitner, the German Physical Society and the Austrian Physical Society have initiated, as Monika already mentioned, the event series Lise-Meitner-Lectures as a joint project, which took place for the first time in Berlin and in Vienna in 2008. This annual series of events, organized by the two societies, aims to introduce outstanding female scientists from Germany and from Austria to a broad audience, as we hope are present today. The Lise-Meitner Lectures are held in Germany, usually during the annual conference of the German Physical Society, but this year, next year, it will be outside the annual conference, and in Austria, outside the conference, annual conference. And these Lise-Meitner Lectures are intended to arouse interest in physics among the general public, and especially among girls and women, and to help reduce prejudices and ignorance about natural science. So the impact towards science should be increased, and the interest for science should be increased. So I hope you will enjoy this lecture, which will be given by Claudia Draxl, and I hand over to Monika.
Thank you. One more thing. I would like to dedicate this lecture, today's lecture, to Dr. Karl Riedling, who was the General Secretary of the Austrian Physical Society from 2011 to last year, and he died prematurely, and we all miss him. He supported me very, very much in very many Lise-Meitner-Lectures. I'd like to dedicate this talk to him, and we have also invited his widow, Evelyn, as a special guest of the Austrian Physical Society today. Now, finally, we come to the most important person today, being Claudia. I have known Claudia for a very long time. In fact, it was the Austrian Physical Society who brought us together, and we are very good friends. We have been friends for decades, but it was the work group Women in Physics, as it was called at the time in the early 90s, that brought us together. I was in Innsbruck, she was from Graz. We worked very hard to find new ideas and ways how to promote women in physics in Austria, which wasn't easy at the time, believe me. It's much different from what it is now. Anyway, so I know her have known her for a really long time, but I still have to say, apart from being a great person and a true friend, she's an awesome researcher with a lot of really very outstanding results and initiatives. It is really remarkable what she's been doing. She did her PhD at the University of Graz in physics, and then was early given an honorary doctorate and a guest professorship in Sweden at the University of Uppsala. After a while in Graz as an assistant, she moved as a full professor to the Montana-Universität Leoben, but this was just a stepping stone for her to become a full professor, the Einstein professor at the Humboldt-University of Berlin, where she has been since 2011. She holds a number of awards in her field, being solid-state theory, but also numerical modeling of novel materials. For example, at contact of a surface of organic, inorganic, and this sort of thing. You'll hear about it. She holds a number of prestigious awards. This is just a small selection I made. It's the Ludwig Boltzmann Award, an early award for young researchers, the highest award, the highest distinction that is given out by the Austrian Physical Society in the field of theoretical physics. She received this in 1995. And then she is a fellow of the American Physical Society, which is a very prestigious thing to be. She holds the Science Award of the Federal State of Styria. She's a Max-Planck fellow at several institutions, had that twice, in fact. She's a corresponding member of the Austrian Academy of Sciences abroad, since she's not in Austria anymore. And also her native town of Villach have given her the special Paracelsus ring, which by itself is also a very prestigious thing to get, I understand. So with this, I just point out that we will gather questions at the end of the talk. You can also ask in German, of course. We have set up a special tool. We gather your questions and we have them answered at the end. And with this, I finally hand over to our most special person here today. Thank you.
So thank you very much for this very warm welcome and organizing all this here in Innsbruck. I'm really overwhelmed also to be here in person. It's the second conference actually after after the lockdown, and it's really a pleasure to be here and to talk about to guide you through a little tour through a, for me, fascinating universe. So, if you think about the universe, then you typically think about reaching out to the stars and exploring their colors, their shape, their unusual properties. I brought different stars with me, and you see here a few gemstones, actually. Well, interestingly, this is exactly the same material, aluminum oxide, if you like, but just a little bit of dirt, of impurities, gives them the color. So it's less than 1% of chromium, which makes the ruby red, and other, like iron and things like that, that form the other colors. Just less than 1%, which changes the physics, or at least this color of these materials completely. Now, maybe your favorite gemstone is not ruby, but diamond, or maybe you're more interested in gallium oxide. So this is a very fascinating material because it's supposed to be one of the, let's say, best candidates that we have for our future power electronics. This is aluminum nitride. This is used for transporting away heat from materials. That's why it's used in thin films, in coating of materials. Or maybe you just look at graphite. We all have it in our pencils. Let me take out two of them. This is diamond and graphite. What makes them different, or what do they have in common, right? So actually both of them is pure carbon, nothing else like this, but diamond, you see, it's a high band gap material. That's why it's transparent. It's very hard, the hardest mineral that we know. On the other hand, you have graphite, which is black, which is metallic, which is extremely soft. Otherwise, we couldn't use it in our pencils. Right? So let's zoom in into this universe, and then you see how the carbon atoms are arranged in diamond. So it's a very highly symmetric cubic structure, whereas in graphite, they are arranged in hexagonal planes, which are held together by very weak van der Waals interactions. So it's a layered material, and this interaction is so weak that you can even peel off an atomically thin layer of it, and this is what the famous material graphene is about. So you just take a Scotch type, you put it on graphite, and you peel it off, and you can take one atomically thin layer off. And there you see from this picture that you can resolve here experimentally the atoms. So here you see the hexagons of this layer. Now, having such a layer, it was just mentioned before, the buckyballs. Actually, you can also form buckyballs 660 out of carbon, or you can take this graphene plane and wrap it up and form a carbon nanotube out of it, or you can even fill these nanotubes with organic molecules and make them light-emitting nano-object. Again, you can see this experimentally here. This is the TEM picture image, where you see the molecules inside the nanotubes. So this is just one material, but you see just from the arrangement of the atoms, the next neighbors and so on, you can change these properties completely, right? But you can use the whole toolbox of atoms that we have, and there you have a Lego box of building blocks where you can put together any atom with any other in order to form a new material. So you can dream of any material you can think of. And interestingly, so this periodic table of elements is a genius arrangement of these atoms. You have these rows and these columns, and you can, just from the position of this atom, you can read out already the properties of these atoms, and you can guess, for instance, if you combine it with something else, what kind of properties this material might have or not. So there are always surprises, right? So, and this gives rise to a number of, infinite number of different materials. I think we know about 20,000 inorganic materials that have been synthesized, but taking this combination of atoms and also arranging them in different ways according to symmetry and arrangement, this gives rise to an infinite number of them. So far so good, but there is also another thing that somehow creates a quantum puzzle, right? So in principle, atoms consist of nuclei, positively charged particles, and negatively charged electrons. So the interaction between these particles is pretty simple. So it's just Coulomb interaction. That means the nuclei repel each other, the electrons repel each other, but the nuclei and the electrons, they attract each other. And depending on how you arrange the atoms, this interplay of this repulsion and this attraction makes these materials just fascinating. So, but as I said, it's pretty simple because it's just one interaction, one type of interaction, and you may wonder why these condensed matter systems are then so complicated. Right? So, because it's one type of interaction, however, this interaction shows up in very different facets. So, for instance, we have exchange interaction that tells us what happens if you exchange two identical particles. You have correlation, that means if you move one electron, you could guess or not how all the others follow these electrons, how they are correlated with each other. There's screening, because electrons sitting close to each other, they will repel each other very strongly. However, if this other electron is far away, there are many other particles in between which would screen this interaction. So, again, another facet of Coulomb interaction. If you excite a system, this will have finite lifetimes, and so on and so forth. So I just go through it. For instance, spin makes materials magnetic or not. So there's a lot of different interactions. For instance, vibrational coupling that tells you if you move away your nucleus from the equilibrium position, how would the electron cloud follow, and how would the properties change if you do so. So, yeah, finally, spin-orbit interaction, the dispersion forces of van der Waals interaction, which I said before, holds together the graphene planes in graphite. So, again, summarizing, we have these Lego blocks, these the atoms that form building blocks. You have the symmetry and the arrangement of atoms. Now you have these different interactions, which make the whole world of materials really fascinating. So then we can go to our society finally, because there's hardly anything you touch or you think of in our daily life which is not concerned by materials, right? You want to drill a hole, you need a tool. And if you want to become better, because materials are getting harder, you need a better tool, so you need a new material for drilling, right? So you would like to have more lightweight materials. If you fly an airplane, it consumes a lot of energy because these materials are so heavy. So making something lighter, you need something new. And yeah, unfortunately, lighter materials are very often brittle, and you don't want the airplane to break apart in the air during the flight. So you want to make sure that you design the material such that they are not brittle, but still being lightweight and tactile at the same time, which is actually a great challenge. Well, we all love our gadgets, so we want to have our cell phones thinner and thinner and probably curved in order to fit into your pocket. Yeah, this is a very nice slide actually, which is a few years ago old already. Was a work by our colleagues in Linz, which formed the first edible transistor made out of edible materials. So, and it's remarkable. Think about carotene or coffee. And there are a lot of molecules from the organic toolbox that have exactly the same properties like some inorganic semiconductors. And they said this was a field effect transistor out of edible materials, and maybe in the future they said if you don't like your cell phone anymore, probably you can eat it. I don't know. So anyway, energy saving, so think about our lighting systems. So the advent of LEDs was only possible by new material, gallium nitride at the time. Still there is room for improvement because there's still a lot of heat that is produced by our lighting, and that could be saved if you have something better. Well, last but not least, maybe something you don't even think about. If you like a new tooth or a hip or something like that, probably you need a material that somehow fits to the body and is biocompatible. So if you think about our environmental problems and energy problems, I think time is really ripe to speed up this process. And I would like to show you first how our daily research works and how we can describe things. So what is the role of theory and all that? But then I would like to change gears a little bit and tell you how we believe in future our materials research will look like. So, let me state, of course, if you come up with novel materials, then these materials are not so simple anymore, like having one carbon atom in a unit cell, but they may be very complex. So the most innovative materials are nanostructures or large system cells, which of course make the theoretical description also very cumbersome. So the methodology is getting utterly complicated. At the same time, it's also great to see that the experimental resolution is getting better and better. So experiment can tell us right away whether our theory is good or not, or whether probably have forgotten one or the other interaction that I mentioned before, which was not obvious so far because the experimental resolution didn't allow us to tell how good our theory is. So this is very exciting times because you can probe whatever you do theoretically, also from the experimental point of view. So, how do we describe this? So, let me give you a 101 in a nutshell, so to say, on theoretical solid-state physics. So, how can we describe this complicated problem of a many-body system? Well, in principle, we know what to do. It's very simple. So we have a very simple-looking equation. So some of us love Schrödinger, and because, well, in previous times, maybe some of us still remember that this was the most precious money that we have, the 1,000 shilling shine. But some of us love Schrödinger because of this very simple-looking, seemingly simple Schrödinger equation. You have an operator that acts on a wave function and gives you the expectation value of this operator times this wave function. Now, very beautiful, very elegant, was a genius invention, this theory. However, it's numerically not tractable, so it's NP hard, like the mathematicians say. That means that you can only solve it for very few, very small systems. So why is this so? Because if you have a system of n atoms in your unit cell and m electrons, which is typically larger than, of course, than the number of atoms and nuclei, then this wave function and also the operator, of course, depends on the coordinates of all these particles. So every particle is interacting with any else. So, and this is not feasible to do, so we can do a trick by somehow freezing in the atomic coordinates, because they're moving much slower than the electrons, but still you end up with a many-body system of electrons, right? So could be hundreds or thousands in a unit cell. So how to do so? Well, in fact, nobody has seen a real wave function so far, besides some of the Swedes in 1901. You see here, this is even before the Schrödinger equation was born. Sandviken, obviously, this is a steel company in Sweden, was very forward-looking and produced a wave function, to tell us how the future life will look like. So, but apart from this, let's go back to our theory. So, what do we want? We want a theory that allows us to treat all materials on the same footing, and that gives us all the properties on the same footing. So Schrödinger equation would do it right away, because if you have the many-body wave function, you take the expectation value, and then you get any property out of it. So take an operator, you get the property out of it. So now we learned there's no way of getting this wave function, so we have to find another way to deal with this. And this is why I want to introduce, just in 2 lines, again in a nutshell, what density functional theory is about, because this is the workhorse of computational material science. So it's as simple as this, because we know that we cannot treat the system of interacting particles where every electron interacts with everyone. So we take a step, next step, and say, okay, we introduce an auxiliary system of non-interacting particles. So, and what do these share? They share the electron density with each other. So, but having a system of non-interacting particles allows us to boil down this many-body equation into an equation that only depends on 3 coordinates, x, y, and z. So depend only on the electron that you're looking at. So in fact, this helps tremendously because then you only have a very simple equation. Kinetic energy, external potential is basically the potential of the nuclei. You have the classical Coulomb interaction, and then you have the quantum mechanical bit of the Coulomb interaction, exchange and correlation effects. This is the only approximation you have to do, right? But otherwise you have a one-particle equation, you can solve that, right? And this is the essence of density functional theory. So you have to be a bit cautious because, of course, since this is an auxiliary system of non-interacting particles, you cannot interpret the single particle energies and wave functions straight away. So just caution here, but otherwise this is a great theory. And this actually is density functional theory. Mathematically it was proven in 1964 by Hohenberg and Kohn. And the reason why we love this so much is because now we have one equation that we can apply to atoms, molecules, clusters, bulk crystals, surfaces, interfaces, any kind of nanostructure is always the same equation that we solve. And since we get the electron density out of it, then we can avoid computing this many body wave function and get all the properties right away from this electron density. So far so good. This is, let's say, a theory for the ground state. But it helps us actually now to treat systems that contain, for instance, up to 1,000 atoms in one unit cell. So we have this periodic replica, and inside one of these unit cells we can treat around 1,000 atoms, at least with low approximations for these exchange and correlation effects. Now, there are, however, many materials and also many properties. For this is not good enough. So this needs either better functionals, which then, or better methodology. That means that we have to scale down here, because the better the methodology, the smaller the system size is that we can treat. Right? And there you see with the best possible methods that we have, we just can treat around 10 atoms or something like that. So we have to get better. Also, we have to say that these complex systems often require even larger boxes. So I told you before that 1% or less than 1% of chromium makes the color of ruby, so you need boxes probably for some of the properties that are even much larger than 1,000 atoms. It could also be that this requires better methodology. And that's why we have to go in both directions. So we have to somehow increase the number of particles that we can treat, but we also have to make sure that the best possible approximations we have are tractable also for large systems. And this is why there's a lot of efforts going on now to port our computer codes to exascale machines. So these are the computers of tomorrow, in order to make sure that they will be running on these machines. So, going to better methodology, for instance, Green's function methods, is something that we also need if we talk about excitations. So, if you shine light on the material and you would like to know what the response of this material to light is, then we have to go to better methodology. And I like to emphasize here what we're looking at. So, here's the electromagnetic spectrum. Interesting for us is this region here. So, for instance, dealing with X-rays, because X-rays have the same wavelengths like the dimension of an atom. So that means with X-rays we can probe the properties of atoms and also with matter. But what is also interesting for us, of course, is the whole spectra in the visible range, because everything that has to do with color, like lasers or LEDs or whatever, this is something where you need a responsive material in this energy range. So for those who like maths, so the visible range goes from pi half to pi in electron volt. So I don't have the time to talk about the methods. I just tell you that we have implemented all this methodology in our instrument. It's the most exciting computer code you can imagine, because it's called like this, so it's exciting. And it has implemented density functional theory, but also higher level methodology, in particular focus on theoretical spectroscopy. So with this, let's say, introduction 101 into solid-state theory, I just want to give you two examples, so just to see what we can do nowadays with these methods. And the first example is something that we just have been working at, and this concerns resonant inelastic X-ray scattering, so it's RIX. So it's a highly complicated process that I would like to point out in brief. So it combines X-rays and light in the visible range or in the valence range. So that's why it's fascinating. So, I mean, in an atom you have very low-lying electrons. So you need X-rays, high energy, in order to excite them. And this is what happens here in this process. So you have these occupied states here, and then you take these electrons to unoccupied conduction bands. This process is governed by some transition probability. And this probability depends on the let's say, coupling between the states down here and the states up here. But then we also have something that's related to symmetry that tells us the selection rule, so whether this transition is allowed or not. And this gives you the probability of the electron to go from the core states to the conduction bands. Now, this is what the situation is then, because now some of these core states are empty and some of the conduction bands are filled. So, but then you see we have some valence states in between that are filled, and they see these states down there, and this is much more comfortable because this is lower in energy. So they can have the feeling, let's go there, right? So they can drop down, and this is the next process that is involved in RIGS, so such that the populated valence bands are depopulated because they find empty states down here. So again, we have some probability for this process to happen, and this probability is again ruled by selection rules, matrix elements. Again, you find these coupling coefficients that we have seen already, but then we also have coupling coefficients between the conduction and the valence band here, such that at the end, the final state looks like we have now the conduction band populated, we have the valence states depopulated, and the core states are again filled. And this looks like pretty much like it's just an optical absorption where you go from the valence band to the conduction bands. So, and this is the probability here. So, to cut the long story short, what you see here is a result. And this is the cross-section, the double differential RIGS cross-section for gallium oxide. So I introduced this material before. It's not beta gallium oxide that you have seen before, but it's alpha gallium oxide, so a little bit different structure. And, well, in principle, if you just look at the excitation process that happens upon X-rays, then you would get a spectrum like this. So this is an exciton here, and then you see some spectral features. If you just would probe the system with lower energies, then you would get a spectrum like this. And there you see this material has a very large band gap such that the spectrum only sets in at 6 electron volts. So what RIGS is doing, it somehow shows the interplay between these two excitations like we have seen before, right? So if you look at this bright spot here, then you see it's at the excitation energy where we find the very bright exciton feature here in the core level spectra. At the same time, so this is governed by this process here. At the same time, you see that it also probes the interplay between this valence excitation here, which is governed by this process here. So it's an interplay between core and valence excitons. So far, so good. Let's change this material a little bit now, and I get back to this example that I've shown you before. Now this is beta gallium oxide, that this is a little bit more stable than the other one. So on a first glance, you get a very similar that picture here. But if you have a closer look, then you see, okay, now again we see that this bright spot here is coupled with this peak here. So again, this excitation from the core, which obviously is allowed. However, where the peak at the valence spectrum is, this is just dark. And the reason is that this transition is basically forbidden. And this is the interesting thing. So you have the same material, just a little bit different in the symmetry, in the structure. Again, it shows very distinctive features in our spectroscopy. So, let me go to the second example, completely different thing. This is already a work that we published a few years ago from a theoretical point of view. So there were a lot of experimentalists involved, but the experimental resolution didn't allow us to realize this experimentally, and we're still waiting for experimental verification of that. So this is answering the question whether you could see orbitals in an electron microscope. So we have seen before that we can see atoms in microscopy probes, but can we also see orbitals, so the quantum objects, so to say. So for this we look at graphene. Again, perfect graphene wouldn't show you anything. You need a defect, you need a dirty material, so we put a vacancy in graphene in order to highlight this effect. And this is what the electron density of states is, where you see at high energies, so the red color tells you these are orbitals that lie in the graphene plane. At the intermediate energy range, you have mainly pz orbitals, so these are those that stick out of the plane. And at the very low energies, so it's not easy to see, but this green line here tells you these are py orbitals. So again in the plane, but perpendicular to the x. So, and these are the images that you could expect in the electron microscope if you probe low energies, intermediate energies, or high energies. So you would definitely see fingerprints of these different types of orbitals, and as said, we're still waiting for experimental verification. Okay, now let me switch gears and let's go back to history, but then I try to get to future. Now, how do we work? How does our daily work look like? There are many more experimentalists, probably also here in this audience, and now and the experiments were done already some 1,000 years ago. Theory only came into play a few hundred years ago, so after 1600 or so, with the laws of classical mechanics and electrodynamics. What I've been talking about so far was just the solution of Schrödinger's equation, which goes back to the early 20th century. And now I have brought a guest with me, and let's see what this guest tells us. He actually tells us that what I'm telling you is just poetry. So it has nothing to do with reality, and reality is only experiment. So what do we answer this person? So my first answer would be, fine, but now we have computers, and computers allow us to do computer experiments. So it's also kind of an experiment, because we can dream up any material you like, and then we can predict what the properties of the material would be. And this also helps us with density functional theory and other simulation methods to do something which is getting more and more popular nowadays. And this is what we call high throughput screening. So what does this mean? We would like to design a new material without synthesizing it, so we compute a lot of materials and then see whether this material fulfills the criteria we would like it to fulfill. So for instance, if you would like to design a solar cell, you search for a material that has a band gap in the, let's say, range of 1.2 electron volt or something like this. It should have highly mobile charge carriers, and then you can dream up whatever property you like. And then you see whether a material fulfills all these properties, so it goes through here, or whether it drops out at some point. Now let's do this experiment, or this computer experiment, and then we'll accelerate this a little bit. So at the end of the day, we find out we have found 3 materials that fulfill all the properties, so they are gorgeous, they are very valuable, so we will further look at them, but then there may be thousands of others where we close the lid here and we send them to hell. So, But these three, of course, are very valuable, right? So these are taken to heaven. Everyone likes them, so they are further processed, they are synthesized and investigated. So, and this is something we have to think about, because I mentioned before sustainability. So sustainability not only means that we shouldn't throw away all our material and gadgets, but maybe we shouldn't throw away also the results of our research. So, because these thousands of materials are definitely not trash, because we could recycle them. They're just not needed for what we have been looking at, but they may be very useful for something different. So we should keep in mind candidate materials and not throw them away, not forget them, because they could be useful for something completely different. Now, talking about our daily research and what we throw away, I like to bring up also another point. It's not just that we throw away fictitious material, we throw away a lot more. And in order to demonstrate this, I would like to introduce my group to you. So, well, here they are, some of them. So what they are doing, they are all theoretical physicists, so they do paper and pen work, and most of them, they also implement equations into computer codes. All of them at the end run some calculation speed on small computers or medium-sized clusters or in HPC systems. So, what else do they have in common? That, hopefully, at the end of a thesis or a year, they publish nice papers. Yeah? So, I would love to talk about all this, but I don't have time. I just open one of them in order to demonstrate how we work. So, what do we find in the publication? Yes, there's a table, there's a figure, there's a structure, maybe there are a few more numbers, right? But we never ever provide all the information that we have gained during the research we're doing. So if I just sum up here about one possible work, so one publication, a few years of work going in there, maybe several millions of CPU hours, many terabytes of data that have been produced containing all the information about solving this quantum mechanical problem. But at the end, we publish a figure and a table. Can't be, right? So is it worth doing the same again? Because if we remove the hard disk or clean the hard disks of our co-workers, the next one starts from scratch. And they do things again and again, and this happens all over the world, that everyone is doing the same for nothing, right? So, and in order to prevent this, we started to build a materials data repository. So this was the first idea together with Matthias Scheffler from the Fritz-Haber-Institut in Berlin. We created a database just for our two groups for two purposes. So one, for being organized and keeping all the data, but at that time we already had in mind to use artificial intelligence to use this data for further analysis. So, but this was starting 2012 or so, but in 2014 we realized this is so convenient to have this database that we opened it up to the whole world. So we invited people to upload the data to this repository, and since then we have collected now more than 100 million calculations. So this is, if you look it up, the NOMADS, the Novel Materials Discovery Laboratory, where you find all this data. So and this is a shared database where you can upload and download data of computational material science. I would like to just briefly mention this is what we call a FAIR database. FAIR means findable, accessible, interoperable, and reusable. So F is clear, data that are uploaded can be found. So this is okay. Interestingly, I'll tell something about accessibility in a moment. The interoperability is probably the hardest bit of this. So you cannot imagine that 100 million calculations have been produced by one person with the same method, with the same computer code. So in fact, we support 40 different computer codes, and there you see a snapshot of how many calculations each of them will have. So that means that in order to understand what the meaning of the data is, we have to fully parse these input and output files and interpret, so to say, all the numbers that we have in here. So we had to write parsers for all these codes, and we brought them into different file formats and units such that everything is now sitting in this database. We treat data like publications of a manuscript, so all this data get a digital can get a digital objective identifier like a paper, and if you download them, it's under the CC BY license. And as said already, this is a very international endeavor. In the meantime, with collaborations worldwide. So, accessibility. So, to have everything in a common database with the same formats, this also helps us to have data not only accessible through machines or by downloading the files, but also human accessible. Because if you're an experimentalist, you don't look into a file and then see what people write out, right? So you would like to see what people have calculated and what the result is. So that means we have somehow created what we call the Nomad Encyclopedia, where you can choose a material by either selecting its composition, or by properties, or by the formula. Then you get a list of materials that fulfill the properties, and then if you choose one, then you see what people have computed and what the result is. So could be a structure, could be electronic structure, could be phonons, whatever people have computed. So far so good, but now let's get reminded what Max Planck told us. I mean, he keeps reminding us that we're still talking about poetry and we should think about experiment. So, and in fact, since some time we started to also deal with experimental data, but I like to point out how much more complicated it is to do so. And this is with a very, very simple example. It's just the dielectric function of the most simple material you can think of. This is silver. Silver is again an elemental solid, one atom. It's a noble metal even, so what's the problem here? If several people measure the dielectric function, you would expect the same result, but if you look at this here, this is a collection of experimental data. It's not only that the intensity is changing by a factor of 2 or 3 or 5, but the peak positions differ not by milli-electron volt, but even electron volt. So it's horrible, right? So if you want to bring together data from different sources, you basically compare apple and oranges. And even the best possible artificial intelligence method couldn't deal with this, right? So what's the problem? So obviously we have a veracity, very strong uncertainties in here, but we also have variety. And this comes from the fact that you can measure the dielectric function here with very many different techniques. So it could be ellipsometry, absorption, reflectance spectroscopy, or even electron loss spectroscopy. None of these methods so gives you the spectra directly. So there's all these transformation methods behind, which add some veracity because there's approximations, there are models behind, and without somehow taking down the notes, so to say, what has been done in order to achieve the results, you will never be able to compare different measurements, right? You've seen already this bringing these 40 different computer codes together was very cumbersome already, but bringing together experimental data from different techniques and different machines with different resolution is by far more complicated. So, and I emphasized here, of course, we're dealing with different samples because samples could be dirty. Obviously, there's dirt involved, otherwise these measurements couldn't be so different. So, needless to say that we can also compute the same thing, and we can also compute it on different levels of sophistication, again, leading to veracity and variety. So, before going on, I would like to show you one success story of sharing data, so bringing data together from theory and experiment, so from poetry and from reality. And this is the famous story of Johannes Kepler, who actually made use of Tycho Brahe's data to develop his theory of the movements of planets. So we go back to the universe, if you like. So I put a question mark here because it's not so obvious whether they really wanted to share, because personally I think there was some conflicts, but anyway, at the end it was successful by doing so. Now, what we're doing, I've showed you, we can use this residual waste, we can use the candidate materials, now we take care of experiment, describing them in each and every detail. We also take care of the synthesis recipes. If you really bring together all this knowledge, I think, then we really have a gold mine here, so that means this data is a raw material that can turn into gold. Now, of course, you will ask me, how do we do this, right? So let me show you one example at the end. So we go back to history and we go into future now. So what I think the future of our research will never replace these three paradigms of science that we have been talking about, but as a fourth pillar, a fourth paradigm coming up, and this is data-driven science. And this is not an invention of material science, so this is very general discovery from data, which was first coined by Jim Gray in 2007. And of course, we can make use of this in material science, but again, we have to develop new methods. Like here, we were going from the laws, paper and pen work, to numerical methods. Now we have to find methods in order that allow us to identify trends that are in a big heap of materials, data, which we couldn't see with our naked eye. No. So, and this brings me back to the challenges in finding new materials that we had at the beginning. And what we're dreaming about is to arrange the materials in such a way that we can read from kind of a map where we find materials for coating, for superconductors, for whatever property you like. Of course, this will never be two-dimensional, will be multi-dimensional thing. The big question mark is, of course, how to arrange them. So what is the descriptor? What are the descriptors here? So what are the mechanisms, the parameters, the actuators behind a certain trend and the function? No, this is, but the role model actually is the periodic table of elements. So they were linearly arranged in columns and rows such that you can read out the properties at the end. But this is a much more complicated problem, I guess. So anyway, this is what we are dreaming of. In lack of time, I just wanted to tell you, where we are going in this direction and what we need in order to get there. So in essence, there are two things. One is that we need artificial intelligence tools that go beyond interpolation. So if you think about, there's a lot of machine learning tools which are really great. If you take them from the shelf, probably you have 100 molecules, you can predict 1 million other molecules that are similar, and you can predict this with an extremely high precision. Okay? However, we would like to think out of the box, as I said before. If we have candidate materials that we have explored for solar cells, we may predict whether they could be useful for something completely different. So we don't want to stay within superconductors to find new superconductors. We would like to explore the whole material space to watch out whether we can find new superconductors in a completely different domain. So in other words, we would like to find something exceptional. This is the pearl, right? And for this we need models with predictive power. And we also shouldn't only share data, but we also have to share the tools and to document the tools in order to allow others to advance these tools and to go on here. The second thing is that we need, of course, a lot of data, otherwise we will never be able to do so, and that's why we have to bring data together from different sources. But it's not only the amount, the quantity of data that counts, it's also that we need the right data. So in other words, we need not only information about the water around the pearl and the sand on the shore, we need data that carry the information of what the exceptional is. And this is a really hard problem for this, right? So we need the right data, and they need also to be well characterized and high quality. And this is something I would like to address in the very last minutes. I would like to show you somehow how we can assess the quality if you bring data together from different sources. So, but this brings me also to something else to tell you aside. If we search for new materials, we also need to somehow find out what makes materials similar. So if you have a material with a certain property, you would like to find a material with the same properties, but probably you would like to replace a material by something that has been toxic, which is not toxic, or something that is very rare by something that is abundant or so. So how can we find similar materials? And I'd like to demonstrate this with one example here. Again, something very similar. So we have created a toolbox that has implemented similarity measures, and I demonstrate this with the example of the density of states fingerprint, which somehow we follow some work, but we have extended this already quite dramatically. So we have gallium arsenide, for instance, very well known for the red lasers and so on, and you want to find a material that is similar to gallium arsenide. Now, we have been searching through 280,000 materials in our database, and this is what we have come up. Gallium phosphide, you see it's very similar in the valence band structure, a little bit of difference here, which makes the similarity coefficient below 1, so it's 0.83 here. So, but still very similar. Of course, a semiconductor physicist will tell me, so what? I mean, I know this, right? So what they are telling me. Maybe, at least I wouldn't have come up with a material like this, which is also found in our toolbox, where you see, I mean, here you see dissimilarities in the conduction bands and the deep-lying band, but if it's only the valence band range that is counting, this might be a replacement, right? So, but why I'm telling this, because I like to point out that we can use exactly the same tool in order to assess the data quality. And for this I have brought, again, the simplest possible example you can think of, namely silicon. And since we have this NOMAD database, we looked up how many calculations for silicon we have, and it was amazingly 2,625 calculations. So in the ideal world, all of them would be identical, because the density of states of silicon is the density of states of silicon. So let's see what we find. So this is the number of codes that we have been found creating these examples, and this is what we find. So in the first example, we see that we have two calculations from the same code, so that means they have been computed with the same parameters, with the same numerical accuracy. So obviously, the difference is only coming from the methodology. So again, a theorist would tell me, so what? I know that GW shifts the conduction band upwards. Clear. But this is what the machine tells us, so we don't search by hand, but it finds it out, right? So in that sense, we can use such automatized tools in order to explore what the impact of the method is onto a certain property. The second example is we take the same methods, so this is a density functional GGA, but we use two different codes. There you see the similarity is better than before. Ideally it should be the same, but it's not quite. And so what is the difference between these two? One is a full potential all-electron code, the other has an approximation inside, it's the pseudo-potential. So possibly that's the impact, the role of the pseudo-potential that makes these two things different from each other. So in that sense, we are exploring this now, extensions to various other properties, to spectra. We can also use these tools for experimental spectra. And we are also somehow combining this with unsupervised learning in order to find out trends of the data and to learn about data, big amounts of data. So, and this basically brings me to the end. This is my last slide. Since I've promised you, so to say, or I've shown you that we would like to arrange materials in terms of maps, just to demonstrate you that this is not just something that will never be true. So if you go to the NOMAD laboratory and look up the analytics artificial intelligence toolkits, there you find first examples already of classification of materials, for instance, how to tell apart binary materials that crystallize in one or the other phase, to tell about metals from insulators or trivial insulators from topological insulators and so on. So there's a lot of tools already available with examples that demonstrate how artificial intelligence can operate on these huge amounts of data. So that's pretty much it. Of course, everything is teamwork, so this is again a snapshot of the group or part of the group, I know how many there are. Also like to thank the funding agencies. You see here the projects we are working on. And yeah, again, I'd like to thank Monika and everyone who has been involved in the organization. I'd like to thank the ÖPG and the DPG for hosting us and providing me with this honor. And of course, all of you for your attention. Thank you.
Thank you very much for an exciting lecture. So, how does it work with the question tool? Can you go to the next? You see the, maybe you can say how it works? No? No questions yet, okay. So we take the questions from the room. Maybe some people will post some questions on the chat. I knew it, you would be the first one to ask a question.
Well, again, it's a naive question from the beginning of your talk. So you showed all these nice versions of carbon from diamond to ever. So, but these are all carbon things that nature provided us and we found out about it. Would the computer, if you run the computer, would it give new forms of carbon which have new properties which nature did not synthesize, but we could try to do?
In principle, yes. I mean, the question is how complex a structure is. You like to explore. Of course, you can dream up anything, so it's possible. I think for other materials, new structures have been found. I'm not so sure about carbon now, but this is, in fact, this is possible. So you can combine, you can dream up your materials, you explore it, you find it out, and you see what is the total energy of these calculations or of these structures, and how they compare to each other, and then you could find out what the lowest energy structure is. In fact, there's also a lot of metastable phases in nature that can be found. For instance, as I said, a diamond is a metastable phase. So yeah, if you burn your diamond, then it's getting to be charcoal or graphite or something like this. Yeah, which is also stable for probably millions of years. So don't worry, but.
So, how well do your computational high-throughput experiments correlate with synthesis, solid-state synthesis high-throughput experiments? Do you find similar structures, or is there only accidental hits?
I mean, these high-throughput experiments it's not only for finding new structures of one and the same material. That's one thing you can do, but it's mainly done for scanning a lot of different materials very often for a certain structure. So, and different means that, for instance, you take an alloy and you replace one atom by another, and then you can replace it by 10 different species. And you can arrange it in different sequences and things like that. So this is one thing, that you explore some composition range of a material, but you could also look at different structures of different materials just because some of the materials are known for a certain property, and there's another family, and you explore many families. I mean, there's a lot of room for being creative. Right? But it's not only that you just look at carbon and look at 1,000 different conformations of carbon. Probably this is nice. This is more a fun project, or in my scientific curiosity. Whereas I think many of the other high throughput studies is really to find something which has improved properties compared to something that you have already.
So can I use these methods also to sort of, if I, in the experiment or in the lab, you're growing these structures, for example, like thin films on some substrates, and there, what we get very often depends on the details on how we do that.
Exactly.
So can I, from using similar methods, also, predict beforehand, like how this would then, what do I get the material in the right phase? Or is it sort of the right configuration? Can I extend these methods to learn also about something like that?
Sure. I mean, first of all, there's also high throughput synthesis already, where people try all kinds of combinations. I'm not quite sure if I got your questions completely right. So, which methods do you like to you want to predict what kind of material you get if you synthesize it one or the other way?
A little bit, yeah. So
yeah,
sort of
yeah,
like, what if I sort of, certain materials, I don't know, some of those superconductors I have to grow under certain pressures, certain temperatures, partial pressures, whatever. So yeah.
I think synthesis is probably even more complicated than experiment, because there is no real source of a lot of synthesis recipes. Actually, this is one of my waste baskets I didn't have time to go into, but this is really a problem, because first of all, if you have a nice crystal, even if it's perfect, most of the details are not published, how you synthesize it. And there's two reasons for this. One is a very human one, because if you have an advantage, a competitive advantage, you probably wouldn't tell the recipe of the synthesis. But even if you would do so, maybe you don't know all the parameters, because there's also a lot of hidden parameters that you can't control, so probably this publication will be not complete. And in addition to this, if we only publish the success stories, then probably we know what works. We might know or not why it works, but we definitely don't know why other stuff doesn't work, because people, they throw away these ugly samples and they don't publish it. So in that sense, I think it's extremely important to really publish also failures, to record in very many detail what was the apparatus, what is the temperature, what is the pressure, what is the exact process, what is the post-treatment of a sample. So actually we're doing this right now with, not me, but we're extending this project now with colleagues from synthesis, such to make synthesis reproducible and that we understand this process.
Just, let's say, more from the experimentalist point of view, you mentioned Ritsch, and what are the similarities and the differences between resonant inelastic X-ray scattering and resonant Raman scattering?
You're the experimentalist, by the way, but
yes, but I'm not a solid state.
I mean, Raman scattering involves vibrations, right? So in Raman scattering, you probe the vibrational levels. So Raman scattering, you shine in light to the sample, you excite vibrations, and then you probe the light going out, and this light going out will have a different energy because the vibrations consume some of the energy, and so the loss that you have of the energy will give you peaks in the Raman. And the resonant Raman means that if you now somehow scan or excite with different lasers and so on, then you will see where there is the maximum of let's say intensity that you gain. Then you have reached resonance. That means that you really excite with your phone, or you really excite the difference between existing initial and final states. Whereas Ritsch is a process where you excite it's a combination of a core level excitations and the valence excitation. So it's not you also can involve now, but this we have not done yet. You also can, of course, involve vibrational states. This would be the next step, but it's even more complicated.
Next step.
Some more questions from the audience in the chat? Well, if not, okay.
But also related to this rig, so this would be done in a synchrotron where you have an X-ray pulse and an infrared short laser, and then you look at whatever electrons produced or so. I mean, I know there are studies of this with DNA and other type of organic molecules, but you would also do this in a solid, or?
Yeah. I mean, this RIGS experiments, they're mainly done actually, I don't know, for whatever reason, with strongly correlated materials. So this community somehow is biased towards the materials, but I mean, you can really use it also to explore what the interplay between different excitations in any material is. I think it's fascinating because you find things that is neither present in one or the other experiment, but the interplay between them gives you new insight into the excitations in a material.
Thank you so much for answering also. And just a couple of remarks. There's a buffet waiting out there, but before we go there, you're supposed actually to fill in this form. It's all in front of you, so we know who's been sitting where, the regulations we need to comply with. Of course, we won't put you in jail if you don't do so, but we're asking you to maybe fill out the form. And on the buffet, of course, you can eat without your FFP2 mask on, absolutely true. But you're supposed to wear a mask when you're not right at the buffet eating something, just going out or in or moving around the lecture hall or outside. I just have to say that. And with this, there's not much left to do apart from inviting all the people who are here in the room to the little refreshments and the buffet out there, and to say goodbye also to the people who have been following the stream, who have been following the lecture online, and to thank you, Claudia, for a brilliant lecture.